The mathematical and numerical methodology you were building to deal with some of the harder issues in turbulence having to do with noise and statistics and randomness and all the rest, did this take you into other areas besides turbulence?
Well, it got me into data analysis and sampling. And may I describe how it went? So I was trying to find ways of describing turbulent flows, but not by describing only some of the variables and relegating the rest into some kind of noise along the lines of a vortex method. And there's this formalism in physics, the Moritz-Zwanzig formalism, which does exactly that. It basically allows you to pick some variables and derive exact equations of motion for those variables in the sea of all the others. So that seemed to be what was needed. It was also attractive to me because the world in which this works is very much the world in which I used for vortex methods, Langevin equation, Fokker-Planck equations. The first problem was to understand it. The physicists often have a very good insight into the physics, and the right equations and the right proofs, having in mind what they know to be true, but not necessarily a way to explain to mathematicians. And I worked with two very good postdocs, Anton Kast and Ras Kufferman, and with my old friend Ule, and it took us several years to figure out what exactly this was. It turned out to be a statement about conditional expectations, how conditional expectations commute with nonlinear evolutions. But it's a non-trivial statement. And our explanation, actually, many people, physicists use our explanations because they're actually clearer than what the physicists wrote, because the mathematics make things clearer. We also noticed that the mathematical problem of making predictions from partial data, which comes in data analysis, and the problem of decay to equilibrium of non-equilibrium systems, which is what Moritz-Zwanzig is about, are the same. So that gave us some interesting insights. Then we derived some formulas which represented marginals as conditional expectations. Conditional expectations are much easier to calculate than marginals, and that came from the Moritz-Zwanzig formalism, and so that was this discovery. This opens the door to sampling. If you know how to calculate conditional expectations, you can sample a subset of variables and then expand, and subset by subset have efficient sampling methods.
Explain a little more what you mean by sampling here.
The problem of sampling is the problem of somebody gives you a probability density which is known, it's not something which you have to look at, which is known, many dimensional. And you'd like to find samples. You'd like to find independent quantities on the computer which are statistically independent, and whose histograms converge to the PDF which you started from, the probability density which you started from. That turns to be very hard. In typical physics problems, you have these PDFs generate colossal numbers of states. A very small fraction of them is of importance because all the rest have negligible probabilities, and you don't know in advance where they are. So that's a very hard problem, and this is a roadblock in much of scientific computing, in quantum mechanics, statistics, in lots of problems. So we seem to have found the possible handle on that problem. I tried to construct a sampling method with that. It worked more or less well. I'm still working on it, and there's a graduate student working on it. But it was hopeful in some respects. And then came a former student at Berkeley whom I befriended when he was a graduate student 40 years ago. He's now become a distinguished oceanographer. He came up and came to talk about data assimilation in oceanography and meteorology. And the problem there is you have a model which is noisy. You have data which are noisy. You would like to generate somehow, try to get something out of both of them. The standard example is you make a forecast, weather forecast for tomorrow in Berkeley. You predict rain. Tomorrow it's sunny. You open the window in the morning and you see the sun is shining. What do? Means you can't leave it at that, because if you don't do something, you have to your knowledge of the atmosphere tomorrow is insufficient. The forecast for the next day is going to be even worse. You can't recalculate because presumably you've done the best you could, so you have to modify a prediction with the help of data. So that's the problem of data assimilation. Using data and models together to reach better conclusions. That problem is reducible to a problem of sampling, and that's the technology of that. And the difficulty there is exactly the one I just told you, that it's very easy to generate very many possible conclusions, possible samples of your solution. Most of them will have negligible probability, and therefore you'll have to do a tremendous amount of work. So the first attempt we made at that used that sampling technique, which comes out of Moritz Zwanzig, came out of an attempt to look at turbulence. And I worked with Zwimin too. We worked for a year and a half and modified it step by step, and we got something which we call implicit sampling, which is a method for using the data not only to draw conclusions about existing samples, but actually to sample. Basically, to get the data more intensely involved in the process, the computational process. And that's, I think, a success. That's people are using it. It's working in lots of settings, and I'm very proud of it. The next step is going to be what I'm trying to do is use that data even better, even more. Not only to use the data in conjunction with models which somebody thought of to get better conclusions, but use the data directly to generate models. So in fact, it's a natural continuation, getting data more and more involved in prediction and in the sampling process. Of course, I'm hoping that I'll be able, once I do that, I'll be able to turn around and use that in some setting, some kind of setting of turbulence. But of course, the problem is that all that takes a lot of time and work, and I'm getting old, so I may not get there, but somebody else may.
One of the people who's doing this with you is a very good postdoc, Matty Motsford, and he's applying it, he's building it with you and also applying it to lots of areas. If I understand, it's everything from robotics to geomagnetism.
Yes. Sampling is a key issue in lots and lots of practical problems. Robotics is a good example. The robot tries to orient itself, and that's done by sampling and modification by sampling. That's the technique. There are lots of problems in quantum mechanics which are reducible through quantum Monte Carlo, which is sampling problems. It's one of those things which, for a pure mathematician, is trivial in the sense that, okay, you have a PDI, probability density function, it has samples, but the question of finding them is something which is very intensely difficult. It's a roadblock in lots of things. In quantum chromodynamics, it's a problem. There's a sampling problem. You can't do calculations because you can't sample it well enough. So this is basically an offshoot of attempts to look at turbulence and computational probability.